All right, so yesterday we started working on projectile motion, and we talked about the simplest projectile, which is a falling object, okay, something that's just falling straight down vertically. We'd only have one component to its motion, the vertical component. Okay, we looked at the Lexus faster than gravity example about that one. And then we watched a couple of videos on projectiles that are projected horizontally. Okay, and we looked at the Rebel Without a Cause and the Thelma and Louise, okay, cars driving off cliffs examples. All right. What are some things we have to remember about projectiles that are projected at an angle? We did this one yesterday, the Rebel Without a Cause. Sorry, not at an angle, horizontally. Okay. What are some things we need to remember?
That the initial velocity or final velocity.
Not the final. You were right before. Right. The initial vertical velocity. The initial vertical velocity is 0 meters per second because the object is projected horizontally, which means at the beginning it is not moving vertically. Okay? It is not moving up, nor is it moving down at time 0. Everybody with me on that? Okay, so that's the really big thing we have to remember. Okay, these questions can go a number of different ways. The one we did yesterday, we were looking for how far from the base of the cliff the cars would hit. Okay, but I could switch it up and tell you how far from the base of the cliff the cars hit and give you this speed and ask you to calculate the height of the cliff. Right? Then you'd have to work backwards. Right? Or I could give you the height of the cliff and how far they hit from the base and ask you to find the speed they drove off at. Right? There's lots of, what do they call it in math? Permutations and combinations for how that can work. Okay? There's lots of different ways. But there's one thing that you're almost always going to have to calculate in order to solve one of these questions. And what is it?
Time.
Time. Why is time so important?
It's for the horizontal and vertical.
Right. It's the one thing that applies to both parts, the horizontal part and the vertical part. So there's never enough time. You always have to find it. Okay? That's what you got to remember about projectile motion. Time is always going to be a big part of it because it applies to both. All right. So we are going to try a different example this morning. This example I called the bomb. Okay? It has nothing to do with that hot sauce and the First We Feast videos. You guys ever watch those? Okay, you got to watch those at some point because they're really funny. Okay, where they have like the stars and they're eating the hot wings and they get progressively hotter. One of the sauces, numbers 8, 7, number 7 is the bomb, and it's a sauce that's just not. It's not just hot, but it's gross. Everybody has the bomb face when they eat it. You got to watch it. It's called First We Feast. It's great. Okay, so. What we're going to do, this has nothing to do with that sauce, but it's about this meme you've probably seen, where there's a guy riding a bomb. And he's been dropped out of a plane and he's riding it to the ground. It's like this, I don't know if you guys have seen this meme, but it's actually from an old movie called Dr. Strangelove, okay, which is this satire of the kind of the Cold War mentality, okay, where the Soviets and the Americans were kind of at each other's throats, and there was always the threat of nuclear. Wait a minute, that sounds like, yeah. Okay, anyway, so back in the day, that was the big deal. And so this movie was a satire of it. But there's a scene where a lone American bomber is flying deep into Russia, and they're about to drop their nuclear bomb onto a missile site. And the bomb won't drop. The bomb won't release. So the bombardier runs back to the bomb bay, and he is pounding on this thing, and he's trying to get it to fall out. He sits on it, and he starts wrenching away, and then it releases. With him on it, okay? And his name is Kong, okay? Like King, but not, okay? And he's kind of like a, I don't know, the cowboy kind of a thing. He's even got the cowboy hat. So they drop him out of the plane, and bomb and all, and he rides the bomb right into the ground, big mushroom cloud, and the whole way down, he's like, yeehaw! All the way, like the whole way to the ground. Okay, so it's kind of funny. So we'll watch the video, and then we'll see if we can do the calculations for it. Okay. Also, while you're watching it, see if you recognize any of the voices from something that's, let's say, a little more modern than this movie. Okay, so did anyone recognize the voice? No, I am your father. James Earl Jones. Yeah, he's in there. Okay, so here's what we know, okay? The plane is moving at 200 meters per second, flying straight and level, all right? If you release a bomb out of a plane that is flying straight and level, the bomb's initial movement is all horizontal, okay? And it's the same speed as the plane that drops it, right? So what actually happens if a plane, like if a pilot is not very bright, they continue to fly in a straight line after dropping the bomb. Why will that end badly?
Because the bomb's travels the same.
Yeah, where will they be when the bomb goes off?
Underneath it.
Right, yeah, the bomb will be right underneath them, okay? You don't want to be right on top of a hydrogen bomb when it goes off, okay? So you drop the bomb and then you bank and you go the other way so that you are not in the explosion. All right, so we are going to say that the bomb's initial horizontal velocity is 200 meters per second, okay? And it's going to land or impact 1,800 meters from its release point horizontally. I want you to calculate the altitude of the bomber.
Are we using straight for this?
There will be. Okay, so in case you're kind of stuck to start with, the thing we said we want to do yesterday is break this up into its vertical and horizontal parts, okay? Kind of write down what you know vertically and horizontally and see what you can get. All right, so we said with all projectile motion questions, horizontal ones are the ones we haven't gone over yet, which are projected at an angle. The thing we want to do is break it up into the horizontal and vertical components. Okay? Horizontally, we already know two things. We know the horizontal velocity is 200 meters per second because that's the speed the plane was moving at when it dropped the bomb. So by default, the bomb has to also be moving at that speed. And we know that the bomb is going to travel 1,800 meters horizontally before impacting the ground. Okay? From a vertical perspective, I know two things. What are they?
Acceleration.
I know acceleration. And what else?
Initial velocity.
I know the initial velocity. What is it?
0.
Right. Okay, what am I looking for
Time first.
before that? Or sorry, after that. But after I have time, I'm going to use it to find the vertical distance. Okay, so this is what I want to find at the end. I have to find time first to get it. Where can I get the time? Right, from the horizontal stuff. I've got V and D, so I can just go T equals D over V. 1,800 meters divided by 200 meters per second is going to give me 9.0 seconds, I believe. Okay, so now that I know the time that this thing is falling for 9 seconds, I can now figure out what altitude the bomb was dropped from. Okay, so I'm going to use D equals VI times T plus 1/2 AT squared. VI is 0, so I can just get rid of that. And I just go 1/2 times 9.81 times 9 squared. What does that come out to, guys? I forgot to fire up the calculator.
397.3.
What?
Is it 397?
397.3. Yeah, that seems about right. But we only have, what, 3 significant digits? So 397, we'll say. Okay, so they were at an altitude of just under 400 meters, okay? And they dropped the bomb. Okay, is that making some sense? All right. So, like I said, there's really only about 3 ways I can ask a horizontally projected projectile question.
Would there be another way to solve this using since doesn't it end? Doesn't it have a final velocity? Would it be able to calculate with the other formula? Since it does end, because it has a final velocity, though, would it be able to? Could you use that formula? Or?
Well, if I knew what the final velocity was, I could. But in this case, I don't know what it is. I could calculate it now that I have this, right? Or I could calculate it now that I've got the time as well. I could find it. But it's a lot of extra work when I can do this in one step, right? It'd be perfectly valid to find VF and then use another formula to calculate D from there if you wanted to. Okay.
So I know VI is initially 0, but why isn't VF 0? If it hits the ground, wouldn't it be at 0?
Because that's a separate acceleration. So all we're considering is the falling part.
Right.
When it hits the ground, it's moving at a high rate of speed.
Right.
And then the ground slows it to a stop, right? It doesn't end at 0, because then I would have VI 0, VF is 0,
And that doesn't.
right, and everything would come out to 0 then. Yeah, so it's a separate acceleration. Once it hits the ground, now it's slowing down.
Right.
Okay, making sense? So, like I said, there's about 3 ways I could ask you to calculate the horizontal distance traveled, the vertical distance traveled, or the horizontal velocity initial. Okay? Everyone with me on that? Actually, I shouldn't say initial, the horizontal velocity, because it doesn't change. Okay? Those are about the only 3 things I could ask you. And the only one we haven't done is calculating the the horizontal velocity. But all you do is you get the height and you get the distance here, and then you calculate time, use the distance and the time, and you can get the speed from there. It's always the same steps, basically, for a horizontal projectile. All right, we're going to watch a little bit of bad movie physics, and then I'm going to give you some time to work on that vector assignment from the other day, because I took quite a bit more time than I anticipated on Wednesday going over the labs. Okay.